So, hello everybody. I think it's 1 minute past the hour, so we could start with today's ENLA seminar, which is the first one of 2021. So this is Jörg Liesen from Berlin, and I'm wishing you a happy new year and good afternoon or good morning or good evening, wherever you are listening or seeing us now. So it's a great pleasure for me to introduce today's speaker, Anne Greenbaum from the University of Washington. Anne is widely known in the community, in particular for her work on non-normal matrices and on iterative methods for linear algebraic systems. And in this area, she has written many great and important papers, for example, on the polynomial numerical hull or on the convergence of in exact arithmetic and in finer precision of the conjugate gradient method and of GMRES. So her book, Iterative Methods for Solving Linear Systems, published by SIAM in 1987, has become a standard in this field. And she has also co-authored a book, Numerical Methods, Design, Analysis, and Computer Implementation of Algorithms, which was published by Princeton University Press in 2012. Anne is a SIAM Fellow in the class of 2015, and she has won several other awards, including the Bolzano Medal for Merit in the Mathematical Sciences of the Czech Academy of Sciences and the SCIAC LA Outstanding Paper Prize. In recent years, Anne has been very much interested in the Crouzeix conjecture, and this will certainly also today appear in her talk. And all participants are, as usual, encouraged to type questions in the Zoom Q&A or in the YouTube Q&A. And these questions will be handled today by Stefan Güttel and Melina Freitag. And now, Anne, please go ahead and tell us about spectral sets, numerical range, and beyond.
Well, thank you, Jörg. I'd also like to thank all of the people who put this ENLA series together. I know that we have a numerical analysis research group mainly for students. And when we don't have a student speaker, we often just go to ENLA and watch one of these recordings, which have all been excellent, all the ones that I've watched so far. So I hope this lives up to that. The work that I'm going to talk about is joint with quite a few people that I've listed here. I guess the work that I maybe wanted to emphasize, I won't get to until the end, and that is work that's joint with Michel Crouzeix. Knowing that students, graduate students, are likely to watch many of these things, I've included a good deal of introductory material that I'm sure will be old to some of you, but I think it's a good lead-in to at least what got me interested in this area. Oops. Oh no. Let's see. Oh. Okay. There we go. So as many of you already know, I'm sure, eigenvalues aren't everything, okay? People often believe that eigenvalues are everything and use them for things that they really should not be used for. I was sort of motivated by a question that Nick Trefethen posed: where in the complex plane does a matrix live? It's very nice if we can analyze functions of matrices through their eigenvalues, but the problem is that eigenvalues tend to tell you about asymptotic behavior, and more often we're interested in behavior of matrix functions not asymptotically, but over a specific time range or a specific range of parameters. And so eigenvalues then, or eigenvalues alone, are not the right tool to use. For example, we're often interested in matrix powers, and one can say that a to the k goes to 0 as k goes to infinity. if and only if the spectral radius, the largest absolute value of an eigenvalue of A, is less than 1. And indeed, for K sufficiently large, each new power will reduce the 2 norm of the A to the K plus 1 will be reduced by about a factor of rho over the 2 norm of A to the K. But sufficiently large, what does that mean? What if K is not sufficiently large? What we're usually more interested in is maybe a specific range of K values. So here I've pictured norm A to the K for 2 different matrices that have exactly the same eigenvalues, the same spectral radius. And as you can see, one of them decreases monotonically as I increase K, while the other one eventually will decrease monotonically at the same rate. But up until that point, it grows by, I guess it's about 10 orders of magnitude and does some strange things that eigenvalues alone simply don't describe. This is also important, of course, in solving differential equations. Suppose we have a system of ODEs, y prime equals AY. The solution is y of t is e to the TA times y0. Once again, e to the TA goes to 0 as t goes to infinity. If the eigenvalues all have negative real part, they're in the open left half plane. And indeed, for t sufficiently large, the rate at which norm e to the TA, the 2 norm, goes to 0 is determined by the maximum real part of an eigenvalue. But we're usually more interested in what happens over some reasonable time period. And again, I've plotted norm e to the TA here for t going, I guess, from 0 to 100. For 2 different matrices with exactly the same eigenvalues. In one case, norm e to the TA decreases monotonically. In the other case, it grows by 5 orders of magnitude and does some strange things, and eventually will decrease monotonically at the same rate as this one. But if what we're interested in is what happens during this time frame, eigenvalues aren't going to tell us what's going on. So one can ask, are there other sets in the complex plane to associate with a matrix to learn more about norm f of A? And a natural place to start is with the Cauchy integral formula. So I think we all learned the Cauchy integral formula for scalars. If A is a scalar, then, and if F is analytic in a region, and gamma is a closed curve, a simple closed curve or union of simple closed curves in that region that encloses A, or in the case of a matrix, the eigenvalues of A, then f of A can be written as 1 over 2 pi I times the integral of, well, f of z over z minus A, if A is a scalar. If it's a matrix, it's the same thing. It's just zi minus A inverse times f of z dz. Okay? And in fact, that's easy to derive from, fairly easy to derive from the scalar version. If A is diagonalizable, you can just look in a basis where A is diagonal, and then this is like zi minus lambda inverse, okay, where lambda is diagonal, and then just apply the scalar version. If A is not diagonalizable, you have to do a little bit more work to establish this, but it can be established without too much trouble. And in fact, it holds not only for matrices, but for infinite dimensional bounded linear operators. So if omega is the interior, it's the region enclosed by this curve gamma, or this union of curves gamma, then we can get an estimate of norm f of a we can relate the, let's say, the 2 norm of f of a, or really this could be any norm here. But let's say the 2 norm of f of a, the largest singular value of f of a, we can relate that to the maximum value of f on omega by simply replacing the norm of this Cauchy integral by the integral of the norm, okay? And then we can take the maximum value of norm zi minus a inverse, the maximum value of the resolvent on that boundary curve. This is called the resolvent. And we get this relation, norm f of a is less than or equal to the length of this curve gamma over 2 pi, absolute value of 1 over 2 pi I, the maximum of the resolvent norm on the curve, times the thing I wanted to relate it to, which is the maximum value of f on omega. But one wonders how much is lost by replacing the norm of the integral by the integral of the norm. And of course, that's going to depend on what curve gamma we choose to integrate over. We can take gamma to be any simple closed curve or union of simple closed curves that encloses the eigenvalues of A. So Nick Trefethen's idea was to take gamma to be the curve on which the resolvent norm, the norm of zi minus a inverse, was equal to a constant, say epsilon inverse. We'll refer to that, the set inside that curve, as the epsilon pseudospectrum. And then you get the estimate norm f of a is less than or equal to the length of that curve over 2 pi times the norm of the resolvent on that curve, 1 over epsilon. And that's the relation between norm f of a and the maximum value of f, or the sup of f, on that epsilon pseudospectrum. Well, in many cases, this is a good choice. There isn't by taking gamma to be the curve on which the resolvent norm is constant, you may not lose too much by replacing the norm of the integral by the integral of the norm. But there are other choices one might make. Sets where you might not have to do that replacement of the norm of the integral by the integral of the norm, and where you might be able to get constants that you know are sharp or near sharp, can't be improved upon by other means. And so that's the main topic that I want to talk about today is how to do that. So one candidate for such a set is the field of values or numerical range. Okay, what is that? Well, it's a set in the complex plane. It's the set of values inner product of AQ with Q, where the norm of Q is 1. This is a set that one can associate with any matrix. It's a compact convex set. That's the Toeplitz-Hausdorff theorem. Certainly, it contains the eigenvalues of A, because if you take Q to be an eigenvector, then AQ inner product with Q is just the corresponding eigenvalue. And when A is a normal matrix, that is, if it has a complete set of orthonormal eigenvectors, then W of A is, in fact, just the convex hull of the eigenvectors. But when A is highly non-normal, meaning that maybe it's diagonalizable, but the eigenvectors are very ill-conditioned, the numerical range may contain a lot more than just the convex hull of the eigenvalues. And this is a classic example of a potential aircraft design. Fortunately, this design was never used. We can't blame any of the crashes we've seen on this design. But there was a matrix associated with a potential Boeing 67 aircraft design, and it had some parameters. And those parameters were optimized to make the maximum real part of an eigenvalue as negative as possible. So they found a way to make the eigenvalues lie in the left half plane. The maximum real part was negative 0.08. And asymptotically, that means that norm of e to the TA will decay over time, okay? Apparently, norm e to the TA had something to do with flutter in the aircraft. Unfortunately, that's an asymptotic result. If one looks at the field of values or numerical range, now I'm on a very different scale. On this scale, the eigenvalues of the matrix just look like a dot here near 0, okay? The field of values or numerical range extends out by about 10 to the 7 into the right half plane. And the result is that, yes, eventually norm e to the TA does decay to 0, but before that point, it does strange things. It grows over orders of magnitude. So one would not like this for an aircraft design. Okay, well, that was sort of my introduction to things. Next, I'd like to say something about Crouzeix's conjecture. So I mentioned the numerical range. Crouzeix's conjecture is the following, or at least this is part of it. For any n by n matrix A, or any bounded linear operator on a Hilbert space, and any polynomial f, or any function analytic on W of A, on the field of values or numerical range of A, norm f of A is less than or equal to twice the maximum value of f on the numerical range. Here, norm again denotes the 2 norm, or the largest singular value. And when I put a set down here below the norm, that means the infinity norm of the function on that set. So the maximum value of f on the field of values. Now, the first thing one might ask is, well, is 2 the best possible constant to use here? Seems like a pretty good one, but is it best possible? And the answer is yes. You can see that just by considering a simple 2 by 2 Jordan block, or take twice the Jordan block. Then it's not hard to see that the numerical range of A is just the unit disk, the closed unit disk. And yet, if you just take f of z equal to z, then f of A is A, and the norm of A, the norm of this matrix, is 2, which is twice the numerical radius, twice the maximum value of z in the field of values. Okay, so we can't do better than 2. There are lots of matrices for which this inequality is known to hold. Certainly for normal matrices, you can replace 2 by 1, and you can replace W of A by the spectrum of A. The norm of A is just the maximum, the norm of f of A is just the maximum value of f on the eigenvalues. And for diagonalizable matrices that have well-conditioned eigenvector matrices and have an eigenvector matrix with condition number 2 or less, again, you just write A as x lambda x inverse. Note that f of A is x, f of lambda, x inverse. So the norm of f of A will be less than or equal to norm x times norm x inverse, the condition number of x, times, again, one can replace W of A by simply the spectrum of A. So that's kind of a trivial case. Crouzeix showed that the result holds for 2 by 2 matrices. Okubo and Ando showed that this inequality holds for matrices whose numerical range is a disk. Okay. And of course, any matrix that is unitarily similar to a direct sum of matrices for which the conjecture holds, the conjecture or the inequality will hold for that matrix as well. Just as an example, a rank 1 matrix, say XY star, is unitarily similar to a 2 by 2 matrix block followed by a 0 matrix block. The inequality holds for both of the diagonal blocks, and therefore it holds for rank 1 matrices. There's been some work on matrices of this form. I started this by looking at what I called a perturbed Jordan block, where all of these are ones, and I let this be an arbitrary parameter, and showed that the inequality holds for matrices like that. Daeshik Choi then extended it to allow for diagonal scalings of perturbed Jordan blocks. So these could be any numbers here. And then Glatter, Karula, and Lindstrom noted that, it doesn't have, this is a permutation matrix. It doesn't have to be one that permutes things in this order. You could have any diagonal scaling of a permutation matrix, and the inequality, Crouzeix's conjecture, would hold for such matrices. Finally, Glatter, Karula, and Lindstrom also showed that the conjecture holds for 3 by 3 matrices with elliptical numerical range centered at an eigenvalue. Okay, kind of a narrow class, but it's a class of matrices for which we know that this inequality does indeed hold. As far as general 3 by 3 matrices, or even 3 by 3 matrices generally with elliptical numerical range, it still is not known whether the inequality holds. One could also look at functions for which this inequality holds. Certainly for linear functions, it holds. Why? Well, because for linear functions, the numerical range of f of a is the same as f of the numerical range of a. And of course, for nonlinear functions, this is not true. Otherwise, the inequality would be simple. It's known that the norm of f of a is less than or equal to twice the numerical radius of f of a. That is, it's less than or equal to twice the maximum absolute value of z for z in the numerical range of f of a. And now, since we're considering f to be linear, w of f of a is the same as f of w of a. So this is the same as twice the max z and w of a of the absolute value of f of z. And that's what we wanted to show. A result of Berger and Piercy is that the numerical radius of a matrix, or the numerical radius of a to the k, is less than or equal to the kth power of the numerical radius of a. The numerical radius, again, is the maximum absolute value of z for z in the field of values of the matrix. So since the norm of a to the k is less than or equal to twice its numerical radius, and r of a to the k is less than or equal to the kth power of r of a, the inequality holds for simple powers. And this is an exercise in Horn and Johnson from the same argument. Suppose f of z is the sum cj z to the j, where the coefficients cj are all real and non-negative. And let's say we've pre-rotated the matrix so that the numerical radius, the point with the largest absolute value, lies on the positive real axis. That is, R of A is actually in the field of values. Well, then we can say norm F of A is less than or equal to the sum of these non-negative constants Cj times norm A to the j, which is less than or equal to the sum Cj times twice the numerical radius of A to the j, which is less than or equal to twice the sum Cj R of A raised to the jth power. So all of those are functions for which the inequality is known to hold. Powers, simple powers, and sums of non-negative coefficients of powers. Okay, but that's pretty much a complete list. Maybe, I'm sure it's not complete, but it's a list of functions, the few functions for which we know the inequality holds, and the few classes of matrices for which we know it holds. Now, Crouzeix made this conjecture in 2004. In 2007, he was able to prove not 2, but 11.08, okay? But the proof was complicated. And he wrote in the paper, the constant 11.08 is not optimal. There is no doubt that refinements are possible, which would decrease this bound. We are convinced that our estimate is very pessimistic, but to improve it drastically, it is clear that we have to find a completely different method. In 2017, in a workshop on evolution equations in Crete, I was not there, but this is what I've been told. Cesar Palencia announced that he had proved not 2, but 1 plus the square root of 2, 2.415, as a bound on norm P of A, or norm F of A is less than or equal to 1 plus the square root of 2 times the maximum value of P on W of A. Apparently, the proof he gave was very complicated, and not many people understood it. But Michel Crouzeix was in the audience, and he did understand it. He simplified the proof, and now they have a really beautiful joint paper that I recommend very highly. It's all of 6 pages long, so you can read it fairly quickly. It's easy to read, and it's a really beautiful result, I think. In fact, in 2017, we had an AIM workshop to discuss, problems associated with this conjecture. And you'll probably see a number of people here that you recognize. In case you don't know some of the players, this is Michel Crouzeix. He's a very broad mathematician. You may have heard of him through Raviar, Crouzeix, Raviar, finite elements, and many other places. And this is Cesar Palencia. Okay. At that point, maybe I would pause and ask if there are any questions that have been raised. I'm happy for you to interrupt with questions.
There are currently no questions on Zoom.
Okay. So I would like to say a little bit about the Crouzeix-Palencia proof of 1 plus the square root of 2, because I think their method of proof is pretty straightforward, and it's important because I think it can be used, well, I know it can be used. I've used it for a number of other results. Okay, so again, the paper. Again, it starts with the Cauchy integral formula. That's one of the main tools here. We'll pull the 1 over 2 pi I inside and make this an integral with respect to arc length. So I'll replace d zeta by zeta prime of s ds and get this integral. Then a new idea is to look at the integral of this resolvent-like matrix, not times f, but times the complex conjugate of f. Okay. Now this is a bit different from what's up here. What's up here, f is an analytic function, so we could say, okay, this integral is equal to f of a. F bar, the complex conjugate, is not analytic, so we can't just say, well, this is f of a bar or something of that sort. But this is what it is, and this is the Cauchy transform of f bar. Okay, so that is the function I will call g of a. And their first observation was that if you take this resolvent-like matrix, add it to its Hermitian transpose, that matrix, call it M of S, is positive semi-definite for all S if omega, the region around which we're integrating, is convex and contains the numerical range. And the argument for this was that on the tangent line to W of A, the smallest eigenvalue of M of S is 0. If you move to the side of that tangent line containing W of A, that smallest eigenvalue becomes negative. And on the side not containing W of A, it's positive. Okay, so that's first piece of the proof. From that, they were able to show that assuming that omega is convex and contains W of A, let F be analytic in omega with infinity norm at most 1, then norm F of A plus G of A star is less than or equal to 2. And again, the proof is not very long. Here's a sketch. Just look at any two unit vectors, u and v. Look at u star f of a plus g of a star times v. Well, that's the integral of u star times this Hermitian matrix, the resolvent, plus its Hermitian transpose, times v times f. Replace the absolute value of that integral by the integral of the absolute values. Use the fact that M of S is positive semi-definite and that the integral of M of S alone is twice the identity, with some algebra to show that indeed the integral of the absolute value of u star M of S v ds is less than or equal to 2. And therefore, so is this, and we get the result about norm F of A plus G of A star. All right, and then the final part of the proof is to relate norm F of A plus G of A star to norm F of A. And again, that's pretty simple algebra. Note that let S equal F of A plus G of A star. F of A star then is S star minus G of A. Multiply on the left by F of A star times F of A, on the right by F of A. And we get this, this equality. The thing on the left, that's the fourth power. The norm of that is the fourth power of the norm of F of A. F of A star F of A times another F of A is less than or equal to 3 times this optimal constant C omega cubed, or is less than or equal to C omega cubed. The norm of S we already showed was less than or equal to 2. Norm F of A star is less than or equal to C omega. And now we've got this H of A, where H is F times G times F. That also has maximum value 1 on omega. So it's less than or equal to C omega. And now we've got this, just divide by c omega squared, and we have this quadratic inequality, which we solve and show that c omega is less than or equal to 1 plus the square root of 2. In fact, what they really showed is that c omega is less than or equal to 1 plus the square root of 1 plus the infinity norm of G, which often is, which they showed to be less than or equal to 1, but it's often, in fact, considerably less than 1. Okay, well, that's all there is to the 6-page paper, the Crouzeix-Palencia proof. Let me move on to the next kind of section of the talk about extremal Blaschke products. Several of us from the AIM workshop then did a workshop working group at Banff. Myself, Pamela Gorkin, Elias Vegert, Felix Schwenninger, Thomas Ransford, and Kelly Bickel. To study extremal Blaschke products. What are these? Well, of course, we're interested in maximizing the Crouzeix ratio. We'd like to know, is this ratio always less than or equal to 2? And we know the form of a function that maximizes this ratio. It's something of the form B composed with phi, where phi is a conformal mapping from W of A to the unit disk, and B is a finite Blaschke product of degree at most n minus 1. What is a Blaschke product? Well, it's something of this form. Can be shown that it maps the unit disk to itself, okay? And well, this is the kind of functions we need to be looking at in order to determine whether this ratio is indeed always less than or equal to 2. So for a given matrix A and conformal mapping phi, we will refer to the Blaschke product, I'll call it B sub E, that maximizes norm B sub E, norm B of phi of A over the infinity norm of B composed with phi, which is just 1 because B maps the unit disk to itself. Phi maps W of A to the unit disk. We'll refer to that as an extremal Blaschke product. So the function f that maximizes this ratio then would be B sub E composed with phi. Well, we've derived a number of different properties of B sub E, or of the matrix B sub E of phi of A. And probably the most important one is that the matrix B sub E of phi of A that maximizes this, okay, has its largest left and right singular vectors orthogonal to each other. Okay, that is, if I take f sub B of A times the right singular vector v1, so that's equal to norm f sub B of A times the left singular vector u1, the inner product of f sub B of A v1 with v1 is 0. Okay, kind of an unusual property, I guess, but that's the property that it has. What are some implications of this? Well, I claim that this implies that for many matrices M, when you add M to f sub E of A, you'll get a larger matrix. Obviously, not all matrices M. You could take M to be minus f sub E of A, and that would not be a larger matrix. But for a lot of matrices, when you add them to a matrix whose largest left and right singular vectors are orthogonal to each other, the norm of the sum of those two matrices is greater than the norm of f sub E of A. if you even look at the norm of f sub e of a plus a matrix M times V1, look at the square of that. So that's sigma 1 U1. Sigma 1 is the norm of f sub e of a plus MV1. And so the square of that norm is this. The only way that that could be less than sigma 1 squared would be if, first of all, MV1 has a component in the direction of U1 with negative real part. And moreover, it would not just have to be negative real part, it would have to be a pretty large negative real part compared to the norm of the entire vector, MV1. So there are lots of matrices, most matrices, if you just generate random matrices and add them to f sub e of a, you'll probably get a matrix with larger norm. And in particular, if you add any multiple, positive or negative or complex, of the identity to f sub e of a, since u1 star times the identity times v1 is 0, you will definitely get a matrix with larger norm, or at least as large a norm as f sub e of a. So what? Well, in some work with Trevor Caldwell and Keenan Lee, we use this to show, to give a new proof of the result of Okubo and Ando, that if the numerical range is a disk, then Crouzeix's inequality holds. That is, norm f of a plus g of a star is less than or equal to 2. What is g of a? Well, it's this integral around the boundary of the disk of the resolvent, zeta I minus A inverse, times the complex conjugate of f. When we're integrating over a circle, we can do some tricks to turn this into a function that we can evaluate analytically, even though f bar itself is not analytic. And you can show that in that case, g of a or g of a star is just the value of f at the center point of this circle times the identity. Therefore, by the previous argument, norm f sub e of a plus g sub e of a star is greater than or equal to norm f sub e of a. And so when we combine that with the Crouzeix-Palencia result, we have it. Okay. We've also done a lot of numerical experiments with this. And we've used a package called ChebFun, which I'm sure many of you are familiar with. We've used it to compute the numerical range and the conformal mapping from the numerical range to the unit disk. And we then use an optimization code to find the roots, alpha 1 through alpha n minus 1, of the extremal Blaschke product. Okay. We choose those roots to maximize norm B of phi of A. Try many different initial guesses for the roots, and then accept the one that returns the largest norm B of phi of A. As I mentioned, we know that B of phi of A has a number of properties, such as its left and right singular vectors being orthogonal to each other. We also know several other properties that it has. So to check our numerics, we can check to see that those properties really are satisfied. Of course, that's never a guarantee that we have the global optimum, but we think we do. And in all numerical experiments that I've run, and I've run many, many thousands, I don't know how many exactly, but many, it has always been the case that not only is it most matrices that you add to f sub e of a that give you a larger norm, But the particular matrix G sub E of A star, when you add that to F sub E of A, you get a larger norm. And since Crouzeix and Palencia already showed that the norm of this matrix was less than or equal to 2, if this could be proved, it would imply Crouzeix's conjecture. More recently, I've actually been trying some other experiments related to this. What happens if you try to maximize norm B of phi of A subject to a constraint, namely that the inequality that I believe holds for the truly optimal B doesn't hold, okay? I force norm F of A plus G of A star to be less than or equal to norm F of A. What would happen then? Well, in all the cases that I've run so far, at least, it finds a point where they're equal, which suggests that if you require that the inequality that I think always holds for the optimal one not hold, then there seem to be even no local maxima for which the inequality in this direction holds. So that's kind of the approach I'm taking to try and prove the conjecture. All right, are there questions at this point?
Yeah, and I think this is a good point to ask a question by Cameron Musco on the Crouzeix Valencia proof that you summarized so nicely. There are two parts of the proof. The first one is to bound the norm of FA plus G star A. And then the second part is to relate this to the norm of F of A. And Cameron's question is it known which of these bounds is sharp, if any? And is the looseness in the final bound caused, is this attributable to one of these two parts in the bounds?
Okay, so norm F of A plus G of A star, if I chose F to be the identity, that would have norm 2. So that bound is sharp. The bound relating norm F of A plus G of A star to norm F of A is not necessarily sharp, okay? I believe in most cases, in all of my numerical experiments, in almost all of my numerical experiments, norm F of A is strictly less than norm F of A plus G of A star. There are a few problems for which those are equal. And I'm not sure I got the last part of the question.
No, so it seems that really the looseness of the bounds is attributable to the second part, right? That
yes,
somehow this G causes trouble in the bound.
yes.
And then Jörg Liesen had a related question. So if this is the case, it seems you get a sharp bound if and only if G is actually 0 or G of A is 0. Would this then perhaps mean that a completely different way of proof would be needed in order to establish the 2 that we actually want, the factor 2?
Not sure I quite get that. So I mean, I believe that this holds, so that if this holds, then we've got it. If adding G sub E of A star to F sub E of A always increases or leaves the norm the same, then we've got it because they already showed that this is less than or equal to 2.
I see.
I'm not sure if I got the question.
Jörg, do you want to say anything else about this?
Whoops, my camera. Okay, no, I was just wondering, when you showed the proof, the final step of their proof, you end up with this bound 1 plus the square root of 1 plus the norm of G, and that is only 2, like if and only if this norm of G is 0. So therefore, I was wondering if their proof could be extended or if that proof could be modified to give the actual bound 2.
Yeah,
Anyway.
I don't see how, but yeah, you're right. Their proof would only give you 2 if G turned out to be 0.
Yes.
And that's the way it is.
Yes.
If G turns out to be small, which it often does, it gives you something better than 1 plus the square root of 2, but still bigger than 2.
Okay, thank you.
Okay, thanks, Anne. There are no other questions currently.
Great. All right. So what about other K-spectral sets where K is this constant 2 or 1 plus the square root of 2 or whatever you can prove? Well, in joint work with Trevor Caldwell and Keenan Lee, we went through the Crouzeix-Palencia result and said, well, what if we have a region omega that contains the spectrum of A, but it doesn't necessarily contain the numerical range? Then for all F that are analytic in omega and have infinity norm at most 1 on omega, what we can show is that if we look at F of A plus G of A star plus gamma times the identity, where gamma involves the smallest eigenvalue of this matrix M of S that was like the resolvent plus its Hermitian transpose, and which had smallest eigenvalue 0 on the boundary of W of A, then the norm of S is less than or equal to 2 plus delta, where delta again involves lambda min of M of S, which will be negative if we're inside W of A, but it will also be positive if we're outside W of A. And so if our region is, say, part inside and part outside, the negatives and the positives may undo each other, they cancel each other, and we may get a very nice result, a very nice constant for that set omega. And the proof of this, again, is exactly like the Crouzeix-Palencia proof, except that you include what the smallest eigenvalue of M of S is, because we can't now say that it's 0. Using essentially this argument, a few more things, Michel Crouzeix and I were able to establish some other K-spectral sets. Let R be the max of norm A and norm A inverse, and consider the annulus whose outer radius is R and whose inner radius is 1 over R. It turns out that that is a 1 plus root 2 spectral set for A. Alternatively, you can take the disk of radius capital R about any point. Here I've got one about 0. And instead of removing a disk, a circle in the middle, I could remove the disk about, in this case, I guess it's -2 of radius 1 over capital R. And that would be a 2 spectral set, a 1 plus root 2 spectral set for A. So using that same line of argument, but taking into account more of what lambda min is, lambda min of M of S is on different sets, we were able to establish some new 1 plus root 2 spectral sets. And I should also point out that here numerical experiments are a lot harder. In the case where we had a simply connected region, we knew the form of the function that maximized the Crouzeix ratio. It was of the form B composed with phi, where phi was a conformal mapping from the region to the unit disk. Here on an annulus, of course, that's not can't be conformally mapped to the unit disk. And so numerical experiments trying to figure out the function that maximizes the Crouzeix ratio on a set like this are much harder. Nevertheless, we didn't have to do numerical experiments because we were able to prove this. I should also point out, someone was asking about this in the paper. The proof I won't go through because it's too long, but it involves a geometric argument. One of the arguments we needed to use was, what happens if you sit at a point on the outer circle here and look at a point going around the inner circle? How much does, if you draw a line between those 2 points, how much does the angle change, the angle, say, with the x-axis, as you go around the circle? So as you can see, you start at angle 0, you go up to the point where this line between the 2 points is tangent to the circle. So this is a right angle here. And so you go up to arc sine of capital R over little r, or 1 over capital R in this case. And one can see that way how much this angle changes as you go around the boundary. We were able to prove a little bit more. Suppose omega is the numerical range minus a disk about a point omega of radius 1 over the numerical radius of a minus omega I inverse, where this disk that we're leaving out is either inside the field of values, so we have this annular-like region, or it could, cut a segment, be a cutout type region like this, or it could even intersect the field of values in a finite number of points and thereby cut the field of values into really 2 separate regions. Well, it turns out that that is a 3 plus 2 root 3 spectral set for A. Okay, we need a little more slack here than we needed with when we were looking at the outer boundary being the norm of A, or the max of the norm of A and the norm of A inverse. Now the outer boundary is W of A, a smaller set, and we have to use a little bit bigger constant. What about some applications? Maybe getting close to time, but well, we can apply this to analyze the convergence of the GMRES algorithm for solving AX equal B. Again, eigenvalues are not the right tool here, or at least eigenvalues alone are not the right tool. If you don't know anything about the eigenvectors, you can construct a matrix with any eigenvalues you like, for which GMRES will make no progress until step n. So we need a different K-spectral set to use in order to analyze the convergence of GMRES. So the residual in GMRES is optimal in the sense that of all kth degree polynomials with value 1 at the origin, it's the minimum of norm P of A times the initial residual. So it's less than or equal to the min over kth degree polynomials with value 1 at the origin of norm P of A times the norm of R0. How big is this? Well, from the Crouzeix-Palencia result, norm RK over norm R0 this quantity would be bounded by 1 plus root 2 times the min over all kth degree polynomials with value 1 at the origin of not norm P of A, but the maximum value of P on the field of values. So we've translated the problem of the convergence of GMRES to one in approximation theory. Take a kth degree polynomial with value 1 at the origin, try to make it small on the field of values. How small can you make it? That gives you a bound on the convergence rate of GMRES. But of course, if the field of values contains the origin, that doesn't help because your kth degree polynomial has to be 1 at the origin. So it doesn't give you anything there. This is a classic example that's been used a lot, the Gurcher matrix. You can access it in MATLAB. Here are its eigenvalues. The black curve here is its field of values, okay, which contains the origin here. So the Crouzeix-Palencia result doesn't help, but if we take out this disk, okay, take the field of values minus this disk about the origin of radius 1 over the numerical radius of the matrix, then we obtained this funny shape set that does not contain the origin, and that is a 3 + 2√3 spectral set for A. So we can describe the convergence of GMRES by saying take a kth degree polynomial with value 1 at the origin, try to make it small throughout this, this black set, and that will give us a bound on the residual for GMRES.
Hi, Anne. Just a quick reminder of the time that you check the time.
Oh, it's probably time.
But of course, now comes something which is also very interesting. Maybe you can go through it quickly.
Probably this makes more sense to use for rational Krylov approximations. Okay, and in a rational Krylov space, you have a fixed denominator, Qm-1 of A inverse, and then you're looking to optimize or approximately optimize over the space Qm-1 of A inverse times the span of B, AB up to A to the m-1 times B. The rational Arnoldi algorithm takes its approximation to f of A times B to be this, where A sub m is Vm star A Vm. It is sort of a near optimal approximation in that you can say that the rational Arnoldi approximation to f of A B is at least as good as the best approximation from the rational Arnoldi space to f of A plus well, the best approximate to f of A as well as f of this restricted matrix A sub m. Since W of A sub m is a subset of the numerical range of A, it follows from the Crouzeix-Palencia result that we can bound this difference by, well, we've got 2 of these, so we'll have to say 2, 1 plus √2 times the best approximation to f among the rational functions in that rational Krylov space, how well you can approximate f on the numerical range by such functions. However, if the function f has a pole in W of A, we would like our rational approximation to have a pole at the same point. For instance, if f of z is 1 minus e to the z inverse, it has a pole at the origin. We would like to have our rational approximation be an approximation to f away from the origin. Well, based on this cutout region, we can relate the convergence of rational Arnoldi to how well you can approximate this function f with a pole at the origin by a rational function with a pole at the origin, but you only have to approximate it on this red set. Similarly, for a different matrix, here I have an annulus. The inner radius looks very small compared to the outer radius, but at least it's far enough away from the origin so that you have a chance of taking a rational function with a pole at the origin and approximating this function on this red annulus. And at that point, I am finished.
Thanks very much, Anne. This was a very interesting talk. And in the interest of time, maybe just one more question by Daniel Kressner. He is wondering if you have looked into complete two spectral sets and if you think there is a significant difference in the sense that the numerical range is a two spectral set, but not a complete two spectral set.
No, I have not. Somebody told me, I think that Daniel Kressner and Crouzeix had looked at that. Can I ask him one? Has he looked at that?
Daniel, are you still around? No, maybe we can take this offline after the talk.
Okay.
Thanks very much.
Thank you.
Yes, thank you, Anne, for this fascinating talk. I think this with the things with the cutout, that was like really very interesting in the end, and many other things too. So thanks for everybody to listening. Maybe Anne, if you stop your screen sharing now, then I can pull up the slide of the following talks. Yes, this one. Okay, good. So thanks, Anne, thanks everybody. This seminar series will continue. The talks are bi-weekly now, Wednesdays at 4 p.m. and we have a great program, as you can see on this slide. Next speakers will be Nicolas Gilly, Dim Nagy, Erin Carson, Gunnar Martinsson, and Cameron Musco. And I hope to see everybody, or at least see the names of everybody in 2 weeks' time, January 27th, and see you then. Bye-bye.